Okay. Well, good morning, everybody. I hope you enjoyed Dixon's lecture on quantum Fourier transform. So now that you've learned a bit, or you've learned about the quantum Fourier transform, we are going to learn about one of the most important uses of the quantum Fourier transform. The quantum Fourier transform is really mostly used as a subroutine within other quantum algorithms, and it is and it's the part that actually provides uh and I think at the end previously we were talking about how we can only use QFT for certain quantum problems, and for you to think about in the comparison between and FFT and DFT. This is where things we need what we need to do is we need to think about how to leverage the QFT smartly. And the quantum phase estimation was one of the algorithms proposed to make use of the QFT in a pretty smart way. So there's going to be a few parts to this lecture. First, I'm going to talk to you about the theory behind the quantum phase estimation. I'm going to go through with you the mathematics behind it, and then I'm going to go through with you a short hands-on a short code. I'm not really requiring this to be a hands-on because I suspect that we might not have enough time for you to try to code things out yourself. But I have provided the code, and I encourage you all to play with it. After telling you all about the theory about quantum phase estimation, I'm going to talk to you about certain applications of quantum phase estimation. In particular, I'll be focusing on one of the most important applications of quantum phase estimation, which is Shor's algorithm. The nice algorithm that everyone talks about when thinking about cybersecurity, and when talking about quantum computing giving an exponential advantage. So, firstly, the theory behind the quantum phase estimation. So, as I said, we always want to start with the problem statement at hand. So, the problem statement for quantum phase estimation is that given a certain unitary matrix, U, and a quantum state, also small u, UCAT, where the quantum state UCAT is an eigenstate of the unitary matrix U, such that it gets a certain phase for it over here. So it's this certain space. And so the purpose of quantum phase estimation is that we want to find the phi in this e to the power of 2 pi I phi over here. Right. So does everyone understand the problem statement here? Does anyone have any questions about a problem statement? It is quite important that everyone understands the purpose of quantum phase estimation and the problem that we're trying to solve. So if you don't understand it, just please put it on please type it on the chat, or just unmute yourself and say something. I'm going to continue first, but if y'all need a reminder, a refresher, or you all have think of questions later, please just type and I will answer. Okay. So given this problem statement, there are a few things that we can piece together in order to form kind of like parts of the puzzles that we have. Okay, so there are a few main assumptions that we have from the problem statement. Firstly, is that we are given this unitary matrix U. It follows that we should know how to implement this unitary matrix on the quantum computer. If you don't, even if you have a unitary matrix, but you have no clue how to implement it on the quantum computer, you are in trouble. The good thing is normally if you know the unitary matrix, the good thing is that normally if you know the unitary matrix, you actually would know how to you will actually know how to figure out how to implement it on the quantum computer. So there are many ways to do that. And that part is actually an active area of research. It follows from the fact that you know how to implement the unitary operation U. It means that you will know how to it means that you know how to perform the unitary operation control U. So does can someone remind can someone remind me what a control operation is? So anyone in the chat? Yeah. So for example, Nima, I think you typed that as uh things. Okay. So yeah, a direct message. Nima sent a direct message to me. I think you make sure that you send it to the entire group chat. Nima said C naught. So C naught is an example of a control U, and Sharif says operation that proceeds only if the state of the control cube if the one qubit is one. Yes. So I think Sharif's answer is a bit more accurate. A control operator, yeah, a control gate is an operation that proceeds only in the state of the control qubit. So you can specify which qubit you want the control qubit to be is 1. C naught is an example of such a control operator. Because where the not is basically the X gate, it's the bit flip gate, bit flip. And so C naught is basically performing the flip when the control qubit is 1 and not performing the flip when the control gate is 0. Okay. This is another interesting part for the quantum phase estimation that is actually quite an active area of research. It further follows that if we know how to perform the unitary operation U, it means that we know how to form the unitary operation control U to the power of 2 to the power of j over here for any j. There are actually I will not be going through exactly how to do this. This is still an very active area of research, and the most efficient ways of doing these are actually pretty difficult to understand. I would recommend people to look at the different ways you can implement phase estimation, like iterative phase estimations, stuff like that online. If you want to find out more how you can do such functions, know that just know that this is something that we can do. Just for now, just know that this is something we can do. We know ways of doing it, and it's active area of research because this is an extremely expensive getting a control U operations and control U to the power of 2 to the power of j can get really expensive. The last thing, which I should really put on a different bigger bullet point is we know how to get the state the UCAT on the quantum computer. So this is the other part. So we are given a unitary matrix U and the quantum state UCAT, which has a certain relationship. We need to know how to be able to perform UCAT on the quantum computer as well. So in essence, when we are given a unitary matrix U and the quantum state UCAT, it means that we know how to implement these on the quantum computer. The next important part of the puzzle is the quantum Fourier transform, which luckily you all just learned in the previous lecture. So this is the code this is the equation that you get for the quantum Fourier transform. This is not the equation that we'll be using later while doing the math, but I think this is the more recognizable equation for those people who do a lot more Fourier transform FFTs and DFTs in their normal work. Okay. More specifically, we'll actually be requiring the use of the inverse QFT, and you also learned how to performed the inverse QFT in the previous lecture, during the hands-on, which is basically which is creating the QFT circuit and then getting the adjoint of the QFT circuit. Okay, the last thing that we'll need to know is that we might not be able to get the exact value of phi. And this is actually often the case. Why is this so? So if we look at here, this phase operation over here, this phi over here, it does not necessarily need to be it does not necessarily need to be some sort of real value or anything like that, or a fractional value or anything like that. It can often be just this continuous values that disappears off to the ends of the f. We will see that a little bit of that during the ends on later. An example of that is, for example, even if it's a fraction, this can be like this phi can be 1/3, which can be represented by 0.333333, and it just continues on. So and I think the other part is that we only need to know phi past the binary point. It means that we don't really care about any of the integer values, any of the ones that's on the left side of the binary point of this binary point. And note that I'm saying binary point instead of the decimal point because we are working entirely in the binary number scheme at this point. So we're not caring about any numbers to the left, we're only caring about numbers to the right. Can anyone tell me why that is the case? Does anyone know why that is the case? I'll give you all a hint. So if you will look at this, it has something to do with the e to the power of 2 pi I. Yes, it's to do with the periodicity over here. So if your phi has any number basically that has numbers past this point, it just means this is just kind of going around the circle, and we are just coming back to the same point in the circle. And so we actually only need to care about the stuff past the part on the right side of the binary point. Okay, great. Okay, so in essence, the QPE algorithm is allowing us to find an approximation up to a few binary points. What that means is that we will need to define a certain precision that we'll have. As we had learned just now inside the quantum Fourier transform, if you have only 4 binary, if your J here consists of a bit string that has 4 qubits, we'll only be able to access to the precision of 0.0xxxx. If it's 5 qubits, then it'll be another x over here, where all of these x's are bits, so either zeros or ones in the binary number scheme. And so we'll denote this approximation by phi 12 on top. And so yeah. Okay, so these are the main pieces of puzzles that we need to remember for the QP. Firstly, that we need to know, okay, to reiterate, we need to know how to implement U, the unitary matrix U, on the quantum computer. We need to know how to perform we need to know how to create the quantum state UCAT on the quantum computer. Given that we know how to implement unitary matrix U on the quantum computer, we can then implement control U and as well as control U to the power of J. Over here, there are many methods to do so that we're not going through. And last thing is the quantum Fourier. The quantum Fourier transform is something that we already know how to do. that I assume that you all know how to perform at this point. I will still be going through a little bit on that later. And that the last thing is that what we are looking for most of the time is an approximation. There are certain cases where it does not necessarily need to be an approximation, and that's when it can be perfectly defined by like for example 0.01 type of thing, and there's no numbers past that. Okay, so very quickly, I'm just going to go through the circuit with you for quantum phase estimation. So it consists of actually three parts. In this picture, you'll find the first two parts. The first part is first just getting a unit is performing a Hadamard transform on the first t qubits. Okay, so we have firstly, okay, maybe I'll start with this. We have two registers that we care about. The first register is the t qubits, the first t qubits, which you can say n qubits, t qubits. This is just a number, however number of qubits you want. And this first register is very important because this defines the precision of your algorithm. If you remember, I said that there's going to be approximation over here. There's going to be approximation. So the number of binary points that you can get after the zero is defined by how many qubits your first register has. Your second register would just be you implementing the quantum state UCAT, which we assume that we know how to do because we are given that within the problem statement. Okay, so the first step, so I guess really the step 0 is just implementing your quantum state preparation for your second register. While you're doing that, you can also perform the Hadamard transform for your first key qubit of your first register. What this gets you is a uniform superposition of states. After performing the uniform superposition of states, we will be doing a control U gates, control U to the power of j gates onto the second register. I will be going through with you all the math and how this results in basically this equation in a short while. But this is the second part of the algorithm. So this is step 2. The last step is then performing the inverse quantum Fourier transform over here. So this is you performing the Hadamard transform. Then you are performing u to the power of j over here. So this is entire thing over here. And inverse Fourier, and then the last step is to perform the inverse Fourier transform on the first t registers again. Okay. At this point, does anyone have any questions? Let's see a couple of messages. Okay, someone has mentioned to me that we might not have used register in this context before. Does anyone not know what is anyone confused by first register and second register over here? Okay, I'm just going to go through with it briefly. If you have any questions, please do ask. So basically, what we are trying to do here is we're trying to think of the quantum computer, think of the qubits that we initialize in the quantum computer into two different parts. The second register over here is us implementing the quantum state UCAT. As of this point, we are not actually going to give any limitations on UCAT because UCAT can take any form it wants. And the first register over here is where we are going to do a bulk of our operations. And so, for example, if your if your quantum computer only has it's only 5 qubits long, it only has 5 qubits, and your second register and your UCAT is only requires 1 qubit. It means that in your quantum computer you can use the first 4 qubits for the first register and the last qubit for your second register for the UCAT. If, for example, your UCAT requires 3 qubits, uh, you only have a 5 qubit quantum computer. It means that your UCAT will take up the last 3 qubits, and then you have your first 2 qubits to use in order to perform your first register, which is going to be kind of like the precision of your algorithm. Okay. So what the 4 lines connecting the second register indicate? No. So UCAT here can occupy as many qubits or as little qubits as it wants. The 4 lines that it puts over here is just kind of a way of saying, okay, it can use more than 1 qubit. It can use more than 1 qubit. It does not need to use more than 1 qubit. It can use an arbitrary number of qubits over here. Okay. Does that make sense? So it does not necessarily just mean 4 qubits. It can use 1, it can use 2, it can use 5, it can even use 15, depending on the use case, really. Have I answered your question? Yes. Okay, great. Okay, so now that we know the circuit, I'm going to go through with you all the mathematics behind it. Yeah. Okay, and I'll be doing it on the whiteboard, maybe the iPad. Okay. Okay, sorry. Okay. So we first, okay, I'm going to first use the I'm first going to be talking about the quantum Fourier transform a little bit. Okay, so if we are given, okay, so previously you all learned from the lecture about the quantum Fourier transform. So if I perform the quantum Fourier transform on something like if I perform the quantum Fourier transform on something like let me think. Okay. X1, X2, X3. What will I get? Pop quiz. Okay. I'm going to write it in the form that I kind of want you to remember it as. And so I'm going to write the first thing, which is x to the power of 2n. Okay, this is which is x to, oh yeah, to power of 2, sorry. Yeah. Okay. So what else? Okay, so what are the other parts to this? Does anyone remember from the previous lecture? Uh, who doesn't really know? Who doesn't really know what I'm asking for? Who does or you don't really know what the answer is? Can anyone say anything? So 0.00. No, I'm asking about I'm asking, so if we perform the QFT on this state over here, where x1, x1, x2, x3 are in basically 0 and 1s. Dikshan gave a formula in the previous lecture about how it's going to look like. How it's going to look like. So I've written the first expression. There's two more expressions that follows after this. Can anyone tell me what they are? Does any or if you don't remember, please just say you don't remember. I will. That's fine too. Tensor tensor 0. Okay, so that's tensor 0 plus e I x3 x2 okay. So that's pretty close. I think okay, I'm going to change it up a little over here. I'm going to write, so this is 0.x. I think just looking through, this is 0.x3. And I think this is going to be easier for your side. 0.x2, x3. Okay, and I think you've probably forgot the 2 over here. Okay. So correct. And what's the last one? Yes. Okay. So I know. Okay. So it's this 2 pi I 0.x1, x2, x3. Okay, I noticed that you're putting x3, x2, x1. I think there's a bit of a difference between what I and Dikshan wrote this as. I think Dikshan previously wrote it in the previous order where he did the QFT on something like where he did the QFT on x3, x2, x1, x0, and so it kind of went in reverse order. I'm kind of going ascending, he went descending. So yeah, which is why you kind of see the difference. You see the difference there. Okay. Yeah. Okay. So this is so right now, what this means is that we perform the QFT on basically x1 to xn. We basically get 0 plus 2 pi I 0.xn 1 tensor 0 plus 2 pi I 0.xn minus 1 xn, so on and so forth until we get okay. So what does the inverse Fourier transform? What does the inverse Fourier transform do? Can anyone tell me? Okay, I'll repeat my question again. Yeah. What does the inverse Fourier transform do? Does? If this is what the Fourier transform, quantum Fourier transform does to x1, xn, what does the inverse quantum Fourier transform do? Any guesses? Anyone wants to take a shot? Okay, let's also do it this way. If you don't know what it does, okay, okay. If you don't know what it does, please. Oh, I see. So reply. Pascal is replying. Pascal. Okay, so the idea is the idea is that if the quantum Fourier transform x on this to give us this, the inverse quantum quantum Fourier transform x on instead this entire thing to give us x to give us this cat instead. Does everyone understand what that means? If you all understand, please put the thumbs up. I see a couple of thumbs up. You have phases in the explanation. Some bit string. Okay. Yeah. Okay, Bash, I see a few thumbs up. Okay. Does anyone not understand what I just said? If you don't understand, now thumbs up or just put on the chat. I don't see anyone. Okay. Okay. I don't see anyone not giving putting a thumbs up and asking if no one understands. So I'm going to continue for now. If you don't understand, please just type it in later. Type it in the chat and I'll go through. Okay. So the important concept now is that with the inverse quantum Fourier transform, we can go instead from this representation over here to back to the bit string representation. Okay. Now we proceed to the QPE problem. Okay. So I mentioned 3 steps just now. Can anyone tell me what was the first step? Does anyone remember the first step? The first step was write bit string as integer. No, I'm talking about inside the quantum circuit. Sorry, I think I needed to be a bit more specific. Inside the quantum circuit, what was the first thing that happened? H gate on all. Okay. Specifically, it's the H gate on all in the first register. So we are going to have the first register and second register over here. I'm going to put 3 qubits for the I'm going to do okay, so over here there's going to be something like that. I'm going to do 3, and then we have U over here. So this is first register, and this is second register over here. And this is this. And the first step is to apply the H gate to all of them. Okay, what does that give us? We don't apply anything to this one. 1, 1, 1. Are you sure? What does the H gate do? Okay, the plus, yeah, it gives us the plus state on the first one. And so I'm going to be writing instead of the plus state, I'm going to be writing in the 0 and 1s instead. I'm going to be lazy and I'm going to be leaving out the constant factor. So you still remember that this one should give us a 1 over square root 2 in front, with 1 over square root 2 in front, all of that stuff. I'm going to be lazy. I'm going to leave out all the constant factors for now. Instead, I'm going to put the constant factor all in front. So this is going to be 2 power of n. So n is the number of qubits that you have. Dot, dot, dot. Dot, dot, dot. 0 loss. Okay. So yeah, this is the H. This is the first step. Okay. The second step is the one that is a bit more complicated. So I'm not going to ask you all to remember that. So the second step is after you have basically your plus states on all of them, you have U. Your second step is to first then do the control. This is U 2 to the power of 0. Then you do U to the power of 1. It's U to the power of 2. Okay, so this is what the second step of the QPE does. And if you kind of go up all the way, if you have more than 3 qubits over here, if you have more than 3 qubits over here, it can go. You can have as many as you want. Okay, so what this does over here, I'm going to say, is for the first. Okay, so for the right, so for this qubit over here, let's think about this qubit over here first. Okay, so you see that for all of these controlled U operators, these are only acting upon this qubit and this register. So this one is only acting upon this one. This one is only acting upon this qubit and this qubit. This one is only acting upon this qubit and this qubit. Okay, so we are going to consider each one in isolation for now. Okay, so right now we have U to the power of 2 to the 0 applied to 0 plus 1 and tensor U. Okay, which this is U to the power of 2, 0 Oh, sorry. C. I'm going to put C. This is control. This is a control. So I'm just going to put C on that. 0 U plus 1 U. Note that I'm omitting the tensor product in this part over here. It's still there. I'm just lazy to write it. Okay. So when the control unit when the control U acts upon this, what do I get? Just remember we went through what the control operator does. So when this control operator is acting upon the zero U, does anything happen? Yeah. Does any okay? You get you no. So yeah, nothing happens basically. So if the first one, it just gets 0U. Now it gets more interesting with the second one because when you apply the control operator, when you apply this control operator to this one, you are effectively applying U to the power of 2 to the power of 0, this one, which is just normal U to it. And so when you apply U to this, we still remember in our problem statement, that we are given that U over here gives us e to 2 pi I by U. Right. So when we apply U to the power of 0 here, which is this 2 to the power of 0 is just basically 1, we get e 2 pi I phi 1 U. Okay. Okay. Does everyone understand this? Does anyone have any questions before I move on? Can everyone see how I got from this step to this step? Okay. Again, as usual, if there's any questions, please feel free to mention it. Okay. Now, I hope that you all can see that basically what this expression, we can rearrange this expression as basically 0 plus e 2 pi I phi 1 and U over here. We can we can take U out over here. We can take U out. U out over here. And instead we are just left and nothing happens to the second register. Instead, the phase has gone back all to the first register over here. Okay, so this is a phenomenon known as phase kickback. This is quite an important part, which is actually pretty interesting because right now you see that normally when you perform a control operator, normally the control of nothing happens to the control qubit, and the changes are normally made to the target qubit. But however, in this case, the target qubit is the one that is left unchanged, while the control qubit is the one that changes. This is a phenomenon known as phase kickback. Normally how you do it, actually, is to first do the Hadamard transform all of it to start with. And so the Hadamard step is actually to enable the phase kickback to happen over here. Okay, so there's I hope everyone gets this concept. Okay, so now this one is for this one. Now we want to think about what happens for CuJ. So J, and I'm going to put for J in basically anything above 1, basically. J can be a value of anything above 1 is an integer. It's an integer. Okay. And so when we apply this to here, this is really defined as us doing e to the power of 2 pi I 2 to the power of j phi over here. And this gives us 0 plus e. I'm just going to put j plus over here. Okay. We realize that even when j equals to 0 here, we still get back the same answer because 2 to the power of 0 is just 1 over here. And so we get back the exact same thing. Now, over here, 2 to the power of j, 2 to the power of j is basically any integer that is kind of like 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, however many that goes. And so when we do 2 to the power 1 over here, 2 to the power of j is 2 to the power of 1, 5, 1 over here. With 2 to the power of 2, j just 6, 2 over here. And so when we perform step 2, we realize that no matter what we do, firstly, the second register remains completely unchanged. Nothing happens to it, whatever. Nothing whatsoever happens to it. The target qubit remains completely unchanged throughout this entire process. So first thing we do is we ignore the second qubit, the second register. We don't really consider what happens to it because we know that it just remains completely unchanged in the second step. Now, what happens to the rest of these over here? So now what we are left with is basically if we have n qubits over here. So if we start with n qubits, the expression that we are left with is this one will give us, after the second step, will give us e to the power of 2 pi I to the power of n minus 1. N minus 1? I think it's n minus 1. Yeah, n minus 1. This one, the second one over here. Okay, let's do a second one here. This one would give us e to the power of 2 pi I 2 to the n minus 2 phi 1. And all the way down, this is e plus e2 pi I 2 to the power of 0, 5. Okay. Okay. Can everyone see that? Okay, okay. I'm going to continue for now. Okay, so now remember previously that we wanted a certain approximation. We know that this will take in the form of 0. Well, I'm going to go phi 1, phi 2, phi 3, dot, dot, dot. It can go on forever because remember this can be a continuous variable. And so we said that we wanted approximation. And this, it really depends on the number of qubits. And so what happens when we do QPE is that we truncate it to the nth qubit. Okay. So normally in this one, it can go on forever. You can go n plus 1, so on and so forth. However, when we approximate it, we truncate it at a certain point where at a certain precision that we want. And so choosing your first number, your first n qubits for your first register is what decides the precision of your answer if you have to approximate. Okay, and so if we were to rewrite it in this, if we were to rewrite it in this form, I think if we were to instead focus on this part, this we can rewrite it as 0 plus 2 to the power of n minus 1 over here, e to the power I, and this is 0.n. Okay, so with this approximation over here, we can rewrite the above. We can rewrite the above first register into this form. How we can see this is that if we take 2 to the power of n minus 1 times basically here, we know that we remember in decimal, right? If we do things in decimal, if we do 10 to the power of n minus 1, and then this one is basically like this is basically like, let's say 0 0.1, 2, 3, 4, 5 over here. If we do times 10 over here, all we do is we move the decimal place up like that, right? And this is what happens in decimal. The same things happen in binary. So if it's 10 to the power of 2, this one, it means we move the decimal point twice. And the same thing happens in binary here. Remember that this is represented currently in binary form. Everything is represented here in binary form. And so what this means is that we are just going to shift this decimal place up to n minus 1 times. And so that gives us basically u1, u2, dot, 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 un minus 1 dot un. But you still remember that because we are working with 2 pi I over here, we don't really care about anything that happens on the left side of the binary point. And so in order to make things simpler, we instead just put it 0 because that's all that is. Any number that's onto the left side of the binary point doesn't really matter. So we just leave it, and it can be 0. It will give you the exact same value if it's 0. 0 point something. Okay. Does this form look familiar to you? Can anyone tell me what this form looks like? Does this entire thing remind you of anything else? Yep. It reminds us of the QFT, doesn't it? When we perform the QFT to the power to xn, to x1 dot 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 xn, we get this form. We get this. Right. We get this entire thing. And now, after performing step 1 and step 2, we get something that looks really, really similar. You notice this one is xn minus 1, 0.xn minus 1 xn, 0.x1 dot 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 xn. We get the exact same thing over here. And so what we do for step 3, as we had established earlier, as we have established earlier, if the QFT brings us from xn dot 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 xn, the bit string representation over here, to this representation on the right, the inverse QFT instead brings us from the expression on the right, this expression on the right over here, back to bit string representation. And so what the inverse QFT, and so the third step is just to implement the inverse QFT, which you all have learned how to do in the previous lecture. Just input on, so we just do the inverse QFT on the first register, and we get back U1, UN. Okay, and then we just measure this, and we get our answer. Okay, this is basically the totality of the QPE. Now we note that this is basically I've set out to find this. I've set out to find phi. I realized that I might not be able to find phi exactly. Instead, I'm looking for approximation up to a certain precision that I can define on my own. And I can do so by just measuring this first register over here. Okay. At this point, does everyone understand what's going on? Does anyone have any questions? Because we have just gone through. Okay. Sorry, you're still grappling the concept of phase kickback. Okay, yeah, great. I mean, that's a great thing to have. Okay. Is there anything in particular that you are confused by? Okay, so what phase kickback basically does is it changes the first register in a smart way, and this only applies to certain control unit arrays. The smart way that it will leave this second one intact. It will leave the second register intact. You notice that nothing changes for this one, and all that happens for the second tensor product over here, I1 tensor product with UCAT, is that the phase changes. And because only the phase changes, we can mathematically we can just bring out the u cat over here.